Okay.
Good afternoon, everybody. It's a great pleasure to introduce my dear friend, Professor Edcarlos Domingos da Silva. Professor Edcarlos is a faculty member of the Federal University of Goiás, a senior PQ research, and the author of more than 60 of well-published works in his field. Today, Professor Edcarlos will speak on non-local elliptic problems via the nonlinear Rayleigh constant with general nonlinearities. Professor Carlos, the floor is yours. Please.
Okay. I'd like to thank this kind of invitation. It's my pleasure to be here in this web seminar. Here today, we talk about some uh, uh, results on elliptic equation. This is a work done with Diego Ferraz from Universidade Federal of Rio Grande do Norte. Now we introduce our main problem here. This in the left side is the fractional Laplacian operator. V is one potential, positive potential, and lambda is a parameter, lambda positive, Q uh, less than 2 and bigger than 1. So this term is concave and another term is convex. The function f is on continuous functions and b is also on potential like the function a. The function f is superlinear at the origin and at infinite, and in general, this function f does not satisfy the Ambroside-Rabinowitz conditions. The weights a, b are not necessarily bounded, and the potential v can be one sine change function. Mathematical context. The fractional operator can be defined via Fourier transform, like this in the identity. And here we can consider some applications. So the main challenge comes from the fact that the sublab space, the continuous the continuous embedded from the sublab space into the Lebesgue space is not verified in general, but use some hypotheses using some unbounded weights and some extra conditions on F, you can record some kind of compactness. The main novel in this approach is to consider the nonlinear Rayleigh quotient without any homogeneous conditions on the function f. This kind of predicate appears also in physical systems. We can consider also systems from geography. And more applications from finance, probably looking for delivery process in differential process. You can look for also for non-local equations in geometry. You can look also for no local diffusion process, imagine process, and fluid mechanics. Preview works. You have that, and after Caê Silva and Marcos Leandro et al. Considered these results in the last years, but in our work, in these works today, is the first one that combine nonlinear Rayleigh quotient with non-homogeneous functions f, side change functions v, and unbounded rates. The main point here is looking for the function f that can be one non-homogeneous function. This is the main challenge in the present world. So this is the main hypothesis on our work. V1, B is bigger than one constant, B minus B. V is bounded, locally bounded, and this CV is positive, given by this infimum. And there is some theta 0 here, set in such a way that this limit is going to be infinite. For the function f, we need more assumptions. B1 says that B is not so large here, according to this hypothesis B1. F1 says that f is subcritical. And in order to consider the Rayleigh quotient, we need to one extra assumption on f prime. F prime is look like that one subcritical condition here also. F2, because f is sublinear at the origin and superlinear at infinity, as I told you before. F is positive for t positive, and f is negative for t negative. Here, in the next assumption, we look for this function that is increasing for t positive and decreasing for t negative. This is the more important assumption in our work, because using this assumption, you can look for for the Rayleigh quotient. It is another assumption in order to apply the nonlinear method. More assumption on A. This A is one potential non-negative in this Lebesgue space. If alpha 0 given by this guy here, so you can apply the horizontal methods, showing that some intervals are finite. The main result is the following one. Under our assumptions, there is one lambda star here, finite and positive, in such a way that our main problem has one ground state solution. One ground state solution is one solution with minimal solution among all non-trivial solutions, in such a way that the energy for the function u lambda is negative, and the second derivative given by this expression is positive. And also, this result holds for any lambda positive less than lambda star. And the circular result, under our assumptions, you can look for another extreme. This extreme is one function, is one parameter, lambda star. Here. In such a way that for any lambda, sorry, just a second. our second result, we can find one bound state solution. This is one solution with finite energy, looking for another parameter here, lambda star, upper lambda star, in such a way that for any lambda in this range, you have these properties. The second derivative is negative. For lambda here, the energy is positive. For lambda here, the energy equals 0. And for lambda in this range, the energy is negative. And finally, we have one multiple solution, one third result. Use the parameter lambda. So under our assumption, we obtain two non-trivial solutions for any lambda less than lambda star. More, for any open set omega, we can look for this fractional Sobolev space here. The norm is given by this expression, and one way you are to look for fractional Sobolev space is using the Fourier transform here. But in our work here, we can use this Sobolev space with rate V using this norm and the corresponding inner product here. So we can prove some embeddings, continuous embeddings. More specifically, there is one constant C so that this inequality holds for any U in X. Compact results using some hypothesis that I told before. This space is continually embedded in the Lebesgue space with the potential B here. And this is in this case the continuous embedding is compact using the hypothesis V3. So you can prove that this space, Sobolev space, is compact embedded in LQA with 8A. The energy functional is given by this expression. The capital F is the primitive of F. So you can look for this guy here, J lambda. This function is well defined in C1. Moreover, the derivative is given by this expression here, where the function U and phi are function in X. So you can look for the Nehari method and also for the nonlinear Rayleigh quotient. The Nehari method is given by this equality here. The first Rayleigh quotient is given by this expression. Is homogeneous in this part. Is also homogeneous in this quotient here, but it's not homogeneous in this part. Also, looking for the definition of Rn here, one function stay in the Nehari manifold in n lambda if this equality holds. So the main idea is to look for the fiber maps of the function R, capital R. So you introduce the function Kn given by this special where the function u is fixed. So you can look for the critical points for this function. So we can consider derivative or this function here, derivative on t, looking for this expression. When q prime of 2 is equals 0, if only if this equality holds. So using the hypothesis F3, we can prove that this equality holds only for only one t, that this t is a function of u. With some simple calculations, we can prove these limits words, kn goes to 0, if t goes to 0, kn is positive, but for t small. These limits also holds, so there exists one unique maximum point t and of u for any function u, no trivial. And the proof is quite easy, because looking for this function on the variable t, this derivative is 0 if only if this occurs. So looking for hypothesis F3 and taking into account this limit and this limit, we have one unique TU such that the previous inequality holds this inequality. So this derivative is going to be 0 only once. So you can look for the next result for any x, for any u in x. There is one unique t n of u in such a way that this equality holds. The functional capital N is one function that is zero homogeneous in such a way that capital lambda n of alpha u equals capital N of u for any alpha. It's easy to prove this because capital N is given by the maximum of R T U for T positive. So we can look for these computations here, proving that capital N is zero homogeneous. Now you can introduce the first extreme value, lambda star, looking for this lambda n. Sorry, because this is the correct definition for the capital lambda here. So looking for this guy and take the info of u for any u different from 0, we have the capital lambda star. Sorry, the lambda star. As I told you before, capital N is zero homogeneous, lambda star is a tanh, and lambda star is positive. So you can look for the all machine of Nehari method in order to looking for minimization sequences, proving existence results for elliptic problems. So we can consider more technical estimates. There is one eta positive small in such way this inequality holds for any u different from 0. So if VK is one sequence in such way that this occurs, so VK is bounded and VKQ converges to one function V, and looking for more calculations, the convergence is strong here. So you can look for this proposition here, in this case, proving that capital N, capital lambda N is attained. The second nonlinear Rayleigh quotient. You define capital R, A, in this ray, is similar in this function, is similar to the last one. This is homogeneous in this part, homogeneous here also, but this is not homogeneous. And also, one function U satisfies these equalities if U has 0 integer. So we can look for this function on the variable t here and take the derivative of this function, looking for the maximum points of this function in the variable t here. So you can look for the derivative. Derivative is going to be 0 once, and we can prove the same result discussed before for the capital RE. Crucial models properties. Using some integration by parts and some calculation, we have this lemma. This function is crucial in our work, proving that capital G given by this goes to infinity when a t goes to infinity. This function is increasing for t positive and decreasing for t negative. So t is the unique maximum point for the function its key e. In the second excellent value, lambda star, upper lambda star, we have this definition for capital lambda e. So this is the correct definition of a lambda upper star. Once more, capital lambda e is 0 homogeneous. This upper lambda star is finite, less than the first one extremely, and this guy is attached. Here, we obtain a relationship between these functional here. This is so easy to verify this equality, but the consequences are too important, because this guy here is 0 if only if this difference is 0, and more if this right hand side is positive, because if only if this difference is positive, and in the same way this negative if only if this is negative. As a consequence, we can prove this corollary here. Tn of u is less than Te of u, and this capital lambda e and this capital lambda n has this inequality for any u different from 0. So you mentioned that also, the capital A and capital N has many properties. Here we collect the main properties for this functional. One function, TU, is going to be one function in the nonlinear manifold in of L. This occurs. One function here, TU equals to lambda, if only if this derivative is equals 0, and similar for the item 3 and item 4. Make some more calculations. We can prove this equality. So this equals 0 if only if this derivative is 0. So you can prove this proposition using the last identity. This identity one. Because if this is negative, if only if the left hand side here is negative. And the same occurs in the third item. Similar results can be improved using the functional capital RE given by this equality. This derivative equals this quotient here. So you can prove this proposition, item 1, 2, and 3. Now you can look for the nonlinear manifold. First, we split the nonlinear manifold in three parts. Looking for this part, this one, and this one. This is the bad part for the nonlinear manifold. So, but for any lambda less than lambda star, the bad part is empty. It's good because in this case we can look for the Lagrange multipliers theorem. So you can study the minimization problems given by this. Using the functional is C1. Using these guys well defined. And using this n plus n minus RC1 manifolds, we can look for minimized sequence for the first minimization procedure here and another info here. The strategy is the same. We can looking for 5 maps here with you one fixed function and t is variable. So t belongs to the nonlinear manifold if only if this derivative is equal to 0. So as mentioned before, it's possible to apply the Lagrange multiply theorem, proving that any minimized u in this part or in this part is going to be a critical point for the functional j lambda. This proposition is crucial in our results because if lambda equals lambda star here, the part part in 0 lambda star here is different from the empty set. It's not empty. But if lambda is less than this guy, this set is empty. The proof is quite easy. We omit the details. Actually, it's easy, but it's plain here in some sentence. If you take one function here, the proof flows by contradiction. If you take one function here, assuming that this set is not empty, for lambda here, we have these two identities. But we use the definition of capital N, capital lambda N here. We use that 10 u of u equals to 1. This is inequality holds because we have this here. One function in the bare part in U0 in particular has stay in the Nehari set. So this equal holds. So we have lambda less than lambda. This is one contradiction, proving that this set is empty for any lambda less than lambda star here. So the lambda star is one important spam value for the Rayleigh quotient. Is the first one in such a way that the bad part in the Nehari manifold arises. The projection on the Nehari manifold is important. For any function u different from 0, we have two projects on the Nehari manifold. One in the Nehari manifold n plus, and another one in n minus here. These projections are defined functions in C1 class. This guy is a local maximum for this function. This guy is a local maximum for this function. And similar results holds for R E for lambda in this range. Looking for these inequalities, we can prove this maximum is positive if lambda, capital lambda E is greater than lambda here. In the next item, you have a different conclusion because this maximum is equals to 0 if only if this occurs, and more. This occurs if only if this maximum is negative. The functional J lambda in general is not coercive, but J lambda restricted to the Nehari manifold is coercive. That is, J lambda goes to infinite as U goes to infinite. And more, the values Cn plus Cn minus are bounded, and actually we can look for minimized sequence for these quantities, and using the weak convergence and make more calculation, we can prove that any minimized gives us one strong convergence of sequence because we have compactness proved in the previous slides. So you can look for the one proof for the first theorem 1. User is going to be one minimizer in J lambda. You can apply the Lagrange multiplied theorem. So this is this parameter mu. In this case, mu satisfy this equality. So since this occurs, the part is empty. So the unique value for mu is going to be 0. So thus the function U0 is one critical point for J lambda. And more, U0 is going to be one ground state solution. For the second result, we have one similar strategy because looking for a minimized sequence, the sequence from converge from one function v0. V0 is going to be one function n minus, is one minimizer for j lambda. You can apply the Lagrange multiplies again. So v0 is a critical point for j lambda. But you have a characterization for the sign of the energy for function v0. The function v0 has positive energy if only if lambda stay in this interval. The energy is 0 only for the case when lambda is lambda upper star, and more for lambda in this interval, the energy is going to be negative. As a consequence, we have multiplicity solution. For any lambda in this range, we have a ground station here and one second solution, bound station here, in such a way that one belongs to n plus and another one belongs to n minus. Since these roots are the solutions u lambda and v lambda are distinct and more. This function has different signs for lambda here in this interval. And this function has different energy signs for any lambda in this interval. Examples. We can look for nonlinearities. Any power function satisfies our assumptions. More general, sum of powers like this satisfies our assumptions. For one second example, you can look for this kind of nonlinearity using the logarithm function. So the hypotheses F1, F4 are verified for this function, but the Ambrosati condition are not verified. Because in fact, for any t bigger than 0, the capital F for this function here is going to be one function like this. So you can prove that the Ambrosati-Rabinovich condition are not satisfied in this example. But our assumption F1, F4 are verified, proving that our result can be applied for this function using logarithm function or more general nonlinearities. More examples for potential and weights. You can prove that our assumptions are satisfied for this kind of potential. A can be one function here, and then one function that is going to be one function like this, or one constant multiplied by this function, for example. Or more generally. In this slide, we say that for the local case equals to 1, the result can be rewrite in this way. When using some modification in our approach, you can look for this problem, proving our results with some more different or some more different conditions on the potential A and B. So our results works again for the local case, this case, assuming that S is what is S equals to 1. Conclusion, you can combine the nonlinear relation quotient with functions f, general function f, that are not homogeneous. Establish existence in multiple solutions. We now understand the capital, the lambda star, the extreme lambda star for existence of solutions. You can look for the signs of any solution given by the previous frameworks. You can look for our problem using sign change potentials V and boundary rates and more. You can prove our results without Ambrasev-Rabinovich conditions. Open problems and perspectives. You can look for this range for lambda bigger than lambda star. This is an open problem. You can extend this kind of problems for more general nonlocal operators. You can consider another different elliptic problems, such as the elliptic system of nonlocal elliptic type. You can look also for more different situations. For example, for semilinear or quasi-linear elliptic problems. And finally, we can also consider more general elliptic problems, no-local elliptic problems with nonlinear boundary conditions. Okay? And thank you for your attention.
Okay. Thank you so much, Edcarlos, for this very nice talk. Please, who wants to do question to Edcarlos, open the audio and open the video, please. Questions or remarks?
Sure.
Any question? Edcarlos, I have a little question. Is there some sense for a problem with the same nonlinearity, the same potential, but change the fractional Laplace for the mix operator, the fractional Laplace plus Laplace operator, like the last Valdinoski articles? Is there some sense? Is it possible to do the same result?
Yes. Everything works for this part because we can look for the Neharim manifold. The unique challenge is to recurve our main results using the Rayleigh quotient is to prove the uniqueness of T and of U. Just a moment. The core result in our problem is to prove just more a moment, to prove that this guy is unique.
Yeah.
Okay?
You
understand?
It's possible to
Yes.
show the unique maximum
I
point.
think that looking for this operator that I told you before, you can prove something like that using our hypothesis F3 or something like that, proving this guy here is increasing in T, because here does not depend on T.
Okay.
But for our problem, you can look for this, some guy like this, and proving that if you T U is unique, everything works. I think it's possible.
Very good. So, more questions? Thank you, Edcarlos, so much again. And
Thank you.
Juan, please close.